we're going to carry on from where we kind of left off. So hopefully you will, if you weren't here yesterday, you'll have gone through and looked at some of the videos. If not, well, here we go. So if we want to work out the gradient anywhere along a curved line, okay, we have this problem, right? That we can't read off a distance that changes in y and a distance that changes in x, because that's across this whole distance here, and we want to know at a point here. Okay, so we've got this equation, this limit theory equation, where to work out this f prime x, which is the gradient of the function of x. Okay, so you can think of as y being the function of x. Okay, to work the gradient out, we have this thing where we basically have this term here, which is the function of, well, let's start with this term here, the function of x at our point that we want to know x. So that basically gives us this point here. Okay, x, and that's the function of x. And then we have this other term here, which is the function of when we add a little bit onto x. So that works out this point here. Okay, so all the top is doing is working out that difference. Okay, and the bottom here is just this difference here. Okay, so that doesn't give us the right answer, but then if we use this limit theory where we basically rearrange this to get some equation, and then imagine what happens when this number here, when this value of the small change, when that gets smaller and smaller and smaller, when it gets to 0, we should be getting the gradient at that point there. Okay, and that's what we did with this example here, which, let's move our little guy out of the way here. Little guy, here we go. This is what we did here. This is what we did here with this function here, which is the function of x where essentially y equals x to the minus 1. Okay, and we went through and we substituted in to this equation here, this is kind of like this thing to work out the gradient at any point. We just put in the function of x, where x plus a small change in x, function of x, and the delta x at the bottom. We did some shenanigans, we manoeuvred stuff around to give us ultimately this equation here, where we got 1 minus 1 divided by x squared plus x delta x. And then we think, well, what happens when delta x becomes very, very small? So when it tends towards 0, this term here, x delta x, becomes 0 when delta x is 0. Okay, so that just leaves us with this part here. Okay, and we've just shown that down here, that that's the gradient of. Okay, so what we're going to do now is we're going to do the same thing, but we're going to work out for a case where we can make up a rule that will allow us to do this without going through all of that shenanigans with the this limit theory. Okay, so we want to work out what we can, if we just have a function where x is raised to any power, what do we have to do to that to work out the gradient of that function? Okay, so we can do exactly the same thing. We put it into this limit thingy, do some maths, and rearrange it to something where we can cancel out all of the delta x's, and then we end up with this equation down at the bottom. Okay, so we'll just this is one of the points where I saw this for the first time. I thought, what? So I've been through it, and we're going through it in kind of like maths form. Okay, so first of all, let's see what we've got up here. So we've got say we've got y equals x to the power of n, where n is any number. Okay, there is one case when this doesn't work, but we'll tell you about that. Okay, this could be any positive or any negative integer. So it could be x squared, x to the power of 5, it could be x to the power of 4.5, 7, 1, 9, 3, 8. Okay, it could be any number. Okay, we're not going to do that example. That'll be done. Okay, and we want to know, we want to plug that into this. So we want to know. So for those that weren't here yesterday, so when we use this term f of x, okay, that's just basically an equation where x is the term in the equation. Okay, so this could be thought of as y equals x to the power of n is the same as f of x equals x to the power of n. Okay, and if we're working out the gradients, the terminology for that is we could say that's f dash of x, or we could say that that is y dash, or a small change in y over a small change in x, dy dx. All of these things mean the same. And they mean what is the gradient. That might be how you spell gradient. Anyway, so what we're going to do is we're going to start with this. So we've got this equation where we've got is equal to when the limit of delta x goes to 0. And then we've got this guy up here. We've actually got our function of x plus a little bit of delta x times x to the n. So minus x to the n. So we're going to, first of all, we put minus, so the function, so f of x, in this case, okay, is that. Okay, so we're just going to put in x to the power of n in there. Yep. And then in this bit here, this guy here, okay, we're still applying the same function, but we're applying it to x plus delta x. So it's going to be x plus delta x, okay, and we're basically raising that to the power of n, okay? And then we divide that by delta x, okay? Now, we need to then do some shenanigans, rearrange that equation, so that we can kind of start to cancel out some of these delta x's, especially from the bottom. Okay, so that means that we can then kind of imagine what happens when those go to 0. Okay, so so we're going to do that now. So this is also now equal to the limit of delta x goes to 0. Okay, but we're just going to deal with the top half first, okay? And we'll deal with this bit here, where we've got x plus delta x raised to the power of n. Okay, so that's just the same as saying this bracket times itself a number of times. Okay? Now you could do it with negative values, then it would be like it was in the example we did yesterday, where it would be 1 over that bracket times itself a number of times. Now it'd be slightly more difficult to work out, but we would get a similar, well, we get the same result. Which you can do in your own time if you feel like you're nothing else better to do. But let's just imagine that n is 3. Okay? It could be any number. We could make it 10, but it would be a lot of work. Okay? So that's would just be x plus delta x, x plus delta x, x plus delta x. Okay, and the top thing would still be minus, it would be minus x to the power of n. Yep. Well, in this case, it would be x to the power of 3. So this is basically if n equals 3. Okay? So if we were to multiply all of these terms out, okay, I mean, I could just give you the answer, but the way I kind of can't, because I can't just multiply those 3 brackets out in one go. So I'm just going to do it in two lots. Okay, so we just ignore this one and just do the first two. So it's going to multiply x by x, delta x by x, and then x by delta x, and then delta x by x. Okay, so that's going to be x squared plus 2 delta 2x delta x. Okay, because we've got delta x times x and x times delta x. And we've just got 2 of those guys. Plus delta x squared. Yeah? But those are now all times by x plus delta x. Okay? Then we can just multiply out this bracket by this bracket. Okay? So that would be times this by that, and this by that, and then this by that, this by that, that. Okay, it's going to get quite messy, so I'm just going to bring that out. So the first one will be x cubed. Yeah, x squared times x. The next one we're going to have 2x delta x times delta x. So that'll be squared. Plus delta plus x delta x squared. So that's that times that. And then we can do the next kind of one along, which would be plus x squared delta x plus 2x delta x squared, and then the last one, which will be delta x cubed. Okay, so it's quite long and horrible, that, right? And that's kind of what we've got in this thing here. Okay, which is in the PowerPoint. So what we can do now is we can think, well, actually, all of this thing has still not taken account of, we've still got a minus x cubed on the end there. Yeah? Happy with that? It's not magic. I've just multiplied out this bracket 3 times and put that guy on the end. Okay? So now we can kind of start to kind of like cancel some of these terms out, right? So x, these are all plus each other. Okay, so x cubed, and the only other x cubed we have in here is right at the end. So we've got x cubed minus x cubed, which is 0. Okay, so we can kind of cancel these guys out with yellow, because you can see yellow. Okay, and now remember that all of this, okay, is divided by is divided by delta x. Okay, so I'm going to try and fit this on the board somewhere. Okay, this is divided by delta x, the whole thing. Yeah. So you can kind of try and see if you can group some of these terms together. Okay, so we've got a 2x delta x squared, and we've got a 2x delta x squared here, so we can maybe get rid of that one and say we've got 4 of those. Yeah, you can kind of do that if you want to, and maybe got a delta x squared, an x delta x squared here. That doesn't cancel with anything. And we've got x squared delta x there, doesn't cancel with anything. So we're pretty much there, right? But now if we just divide through every term by this delta x at the bottom, okay? So 4x delta x squared divided by delta x is 4x delta x. So that goes away, okay? We just keep that there. We've kind of cancelled them all. So delta, so x delta x squared, that's just going to become 1. Okay, so that's going to be x delta x. This guy, however, that whole thing will cancel out. Yeah? Made a mistake here somewhere. And this guy here will cancel out and become 2. There should be 3 of these. So when I multiplied that out, I can't figure out where I've lost those. But you can see. Can you guys see this on things? So when I multiplied out the whole sets of brackets, okay, and then I simplified it, and I got 3x squared delta x plus 3x squared x times delta x squared plus delta x cubed. Okay, so do go over this and see if you can get it right. I've made a mistake somewhere in the one I was doing on the board. But what this means is that when you when you then divide this term by the delta x up here, okay, you end up with lots and lots and lots of terms that have a delta x in them, okay, and only one term that doesn't. So this example at the bottom is if n equals 4, you get the same kind of thing, it's just much, much, much longer, okay, where you end up with, let's see if we could go on to the next slide, that's slightly bigger, maybe. You end up with this term here, so we basically, this is the equation that we're basically working with, this limit to work out the gradient and then making delta x small. We've got x cubed here and an x cubed here and a minus x cubed here, sorry, so those cancel out. And then we've got 3x squared delta x and 3x squared delta x squared and delta x cubed. So when you divide all of these remaining things by delta x, you just end up with 3x squared, which is that term there, because you just remove the delta x, okay? And then all of these terms here still have a delta x in them somewhere, okay? So that then when you say, well, when that goes to 0, all you end up with is this guy here. Yeah? And the important thing is that if you do this with, we've done it with 3, okay, and we've got 3x squared. So what we've done is we've taken the exponent, okay, it was 3, it's now 2, so it's the exponent minus 1, okay, and we've taken the exponent that was 3 and we've just moved it down to the front as well. So the gradient of x squared, so the gradient of x cubed in this case is 3x squared. So if we had a gradient of x to the power of n, okay, our general formula is this thing at the bottom, where we'd have n, the gradient of x to the power of n is n times x to the power of n minus 1. And that is a really key, important thing. So we basically end up with a rule that if f of x is equal to x to the power of n, and this is any number, then the gradient of that function is n times x to the n minus 1. Okay? So just do some examples of that. I can't keep. Oh. Write that down and remember it. Like that's like super important. So if we think about the top guy up here, so let's just look at that. So if you could just let's do a word answer. Okay, so for the first one, I want to know what the function, the gradient of that first function is. Okay, and write it in as you were if you were going to write it as a number in Excel. So something x, then use the little hat thing to raise the power of, or just so we've got f of x equals x. So now we've got kind of some rule for doing this kind of gradient thing. Okay. Now, so you've had 2 lectures on basically getting to this point here. Okay, so we could carry on going through all of these other examples of basically where you don't have that simple situation where you've got x to the n and that kind of stuff. But rather than do that, we'll do that next time. I just want to go through an example of why all this matters. Okay, so this is not going to be in the lecture. So why is calculus useful at all? Okay, so one example of why this is useful is if we have let's have a volcano, right? That's a volcano, right? Volcanoes, you can't see purple, right? Red for volcanoes. Okay. Volcano, yeah? Volcano gives out, that's a rock, right? It ejects rocks out of volcanoes. Okay? One thing you might want to ask, okay, is how high does that go? Okay. Now, what you could do is, you could say, well, some volcanoes, some are ejected at an angle, okay, and then you might want to do some vector stuff to work out the horizontal and vertical components of that. Okay, if you know this angle, okay, and you know this velocity, okay, you could do that, right? Should have done that in Massimo. Vectors, okay, but we're not going to do it. We're just going to say it goes straight up, okay. And I'm going to tell you, well, so one of the things that limits how fast something can be ejected out of the volcano is basically when you throw a rock upwards, it has to displace the air above it, right, to get out of the way, right? And one of the things that is pushing back is the shock wave that you get of that basically bow wave of air trying to get out of the way. So it turns out that one of the limiting things is the speed of sound. Okay, because that rock finds it very hard to go past that bow wave in the air. Okay, so let's say the vertical velocity v is equal to 330 meters per second. Okay, so there are actually cases quite a lot of cases where volcanoes actually erupt faster than that because they're not erupting into air. They're erupting into kind of a mixture of air and rock, and sound travels faster in that medium. But anyway, so let's say it's going up at 330 meters per second. Now, that velocity is a vector. Okay, so those of you that have seen Despicable Me will know that it has both magnitude and direction. Yeah. So by convention, let's make the vertical velocity positive. Okay, so that's plus. Okay. So over time, okay, because we know that speed is distance divided by time. Okay, we know we can then work out how high it goes. Distance, yeah, is going to be equal to velocity times time. Yeah. But that's not going to tell us how high it goes, that's just going to tell us, okay? But there's another thing acting also on this rock, gravity. Yeah? So gravity is acting down. Okay? Okay, so, and it's an acceleration. So it turns out that we can write, and you don't need to worry about the details of writing this equation, but the height at any time, okay, is equal to the initial velocity, okay, times time, okay, and then plus any acceleration that acts on that particle, okay, and it turns out that it's actually 1/2 times the acceleration times time squared. Okay, don't need to worry about that, details of that. So, but we know that our acceleration is what? What's the acceleration due to gravity? 9.8 meters per second squared. And what direction is that? So it's going to be negative. So we know that this is plus 330 meters per second. And we know that this is minus 10, roughly, meters per second squared. Okay. Now, one thing we know, okay, is that what we want to know is what the maximum height is. Okay. So if we plotted a graph against time, okay, and height, okay. So this is, I mean, this is our volcano here, right? Okay. So it starts off here, and then over time it's going to be going up. Yeah, as time carries on, the rock goes higher and higher up into the atmosphere. Yeah? But as it goes up, the rate at which it's going up is going to slow down because we're accelerating it downwards. Okay? So we're actually going to get something that looks like that. Okay? Yeah? So you can see that it's going to reach some maximum height. Okay, here, h max. Okay? And that height is going to be reached when the gradient of the function of height, okay, gradient of the function of height is 0. Okay, so if we could take this equation here, okay, we could rewrite this as this is now, this is a function of time. So we're describing the height as a function of time, and that function is this equation. Okay, and we can think about, well, what are we going to do? We're going to differentiate this equation here. Okay, with respect to time. Okay, and we'll go through some of the details of what we do when because we've got one function v times t, and we've got another function here a times t squared. Okay, and it turns out that when you've got things like that, you differentiate that, and then you differentiate that separately. Okay, so we could do that. Okay, so what is the gradient of this part? So v times t on this with respect to t. So in this case we've got this. You think of this as t to the power of 1. Okay. Okay, we can make t x if that makes x is equal x. X is time. Okay, so it's the thing that we differentiate. So if we use our formula, which was f dash of x is equal to n x n minus 1. Okay, we take n minus 1. If n is 1, what is it? It's 1 minus 1. You must know what 1 minus 1 is.
0.
Yeah. So what's something raised to the power of 0? Is 1. Okay? And what's v times 1? So we're bringing n down to the front here. v times 1 is just v. Okay? So f, in this case, is going to be just v. Okay? And then this part, okay, we've got plus there. It's actually going to be, it's actually going to be a minus because our acceleration is minus, but that doesn't matter. So we move the 2 down to the front here. Okay, so this becomes minus a half a times 2x to the power of 2 minus 1, which is just 1. Okay, a half times 2 is 1. So now we've just got minus ax. Okay? So now we have this equation here which describes this gradient. Okay? And to find that time when it reaches its maximum height, all we do is say that this equation here is equal to 0. Okay? And that gives us the time of the maximum height. Yeah? So we could then say, so we've now got, we've got an equation that says 330 minus 10x, okay, equals 0. Okay? And you can just rearrange that, and that will find you the time is equal to 33 seconds. Okay? So that gives you the time at which the thing meets its maximum height. Okay? And then you could then plug that number. If you know time, you want to work out the height. Okay? You know that variable, you know that variable, you know that variable, you know that variable now. You can plug that back in to work out what the maximum height of a rupture was. Okay? So that's an example of why calculus is so useful. Okay? Because we basically, without calculus, we'd have just been, we wouldn't have had a clue how to work that out. It would have been impossible. So the value of calculus is it allows you to work out an equation that describes the gradient, and then you can use that equation to work out when the gradient is at certain values. Okay, and it's quite common to find out when the gradient is 0. Okay? Good. Right. So we do have a bit of time. So let's get back on track. So that was an example, and it's the kind of thing that kind of questions like in the exam. That's how sometimes questions are constructed, saying, you might be asked to build this equation that describes how something is, proceeds through time or something like that, and then to work out what the maximum height is or how far it falls away from the volcano or something like that. Then you can use that to answer the question. So think of that. Just for the last bit of the lecture. So this is basically a table of common functions. So you can see what we've kind of summarised basically at the beginning. So if y equals some function, okay, if that function is a constant, so for instance, the y equals 2, okay, the gradient dy dx, or you could say f dash, yeah, that is going to be equal to 0. Okay. Okay, and you can go through that, and you can actually so if y is just x, the gradient is just 1. Okay, so that actually fits our rule. Okay, where we've got if the f of x is equal to n minus 1, okay, and if that is just x, that's the same as x to the power of 1. Okay, so you move the 1 down to the front, and that becomes 1 minus 1, which is 0. That becomes 1 times x to the 0, which is equal to 1. That's that example there. X squared becomes 2x, and then x raised to any power, you can use this formula to work out to do the differentiation. Okay? So the last basically 2 lectures have been to get that formula. Okay? And then there are some other kind of rules that we kind of have. So for instance, so not all equations can be described in terms of x raised to the power of n. Okay, so you might say, a special case that e raised to the power of x, if you have y equals e to the x. Okay, this is a special case of the gradient of that graph is also e to the power of x, which is weird, but it's true. And we'll go through some of what happens when you have other variables in there next time. Sin x and cos x. Just do the same thing. So as we're doing here, just sketch quickly a graph of sin x. Okay. And then sketch its gradient. think that's sine. Yeah? Now, think about what the gradient of that graph looks like. Okay? So I don't think that, but if we were to plot on the same, let's just do another. So this is now dy dx. Okay? Now, just mark on the points where the gradient is 0. Yeah? Now, where is the gradient the most positive? It's the most positive here and here. And it's the most negative here. Yeah? So that means we've got a big positive here, big positive here, a big negative down here. Okay? And you can see here that in this portion here, the gradient's not changing much. It's quite constant. Whereas here, it's changing a lot. Okay? So we could think about okay? So you can see how now this is the gradient of this one up here, and that looks like the function cos x. Yeah? So basically f of x, or f of sine x equals cos x. Okay, and you could do that for cos x, so it doesn't go back directly, because in this part of the graph here, okay, we've got a very strong negative gradient. So if we were to differentiate cos x, we wouldn't get sine x back; we'd get minus sine x. So just yeah, so that's that. Okay, so just to wrap up there. So hopefully you should see that we've gone through and we've made a rule for differentiating equations. Okay, so you can take any equation and then work out the gradient of it. Okay, if it's an equation that's x to the power of something, and then there are other rules that you need to consider. Okay, if you don't have a simple equation to differentiate. Okay, and hopefully you've seen the power of this calculus, where you can use differentiation to work out points in time or points in your experiment or along the distance, where the gradients are 0, and that tells you something useful about the system. Okay?